I know people who cannot afford to pay the mortgage on their homes, their car payment. I have personal problems with the national debt, but how has it affected you? And if you have no experience in it, how can you help us if you don't know what we're feeling?
I think she means more the recession.
Tell me how it's affected you again.
You
know people who've lost their jobs and lost their homes? Well, I've been governor of a small state for 12 years. I'll tell you how it's affected me. Every year, Congress and the President sign laws that make us do more things and gives us less money to do it with. I see people in my state, middle-class people, their taxes have gone up in Washington and their services have gone down. Now let's talk solutions. To me, it's pretty simple. We got to invest in more software engineers. We need high-skilled labor in order to compete with the rest of the world. So in tonight's debate, I will lead by example and talk about some basic concepts of software engineering. I would like to take some time to talk about sorting algorithms in particular. A sorting algorithm is a set of steps a computer follows to put things in order, like arranging numbers from smallest to largest. Imagine you have a messy list of numbers, like 4173, and you want them neatly lined up as 1347. A sorting algorithm is just a way to tell the computer how to do that. Even though computers work fast, they still need clear instructions to know what to compare, when to swap things, and when the list is finished being sorted. There are different types of sorting algorithms, and each has its own method. Even though sorting might seem simple, the way it's done can make a big difference in how fast the computer can finish, especially when there's a lot of data. In practice, sorting algorithms let computers organize data quickly so it can be searched, compared, or used efficiently, like alphabetizing names, ranking scores, or loading websites faster. Without sorting algorithms, computers would have to check every single piece of data one by one, which would slow everything down dramatically. Searching for a file, loading a search result, or even opening an app could take way longer, especially with large amounts of data. There are 5 main types of algorithms that we will discuss: bubble sort, insertion sort, merge sort, heap sort, quick sort. First, let's talk about bubble sort. It's a simple sorting algorithm that works by repeatedly going through a list, comparing 2 items at a time, and swapping them if they're in the wrong order, like bubbling large values to the top. This process repeats until the entire list is sorted. Think of it like shaking a jar of mixed marbles. Each shake pushes bigger marbles upward until they're all in the right order. It's slow, but very easy to understand and implement. Let's go through an example. Say we have the list 3, 1, 18, 30, 25. We want to sort it in ascending order. Bubble sort starts at the beginning and creates a kind of bubble around the first 2 elements to compare them. The first 2 elements are 3 and 1. Since 1 is less than 3 and we want the smallest numbers first, the algorithm swaps them. Now the list looks like this: 1, 3, 18, 30, 25. Next, the algorithm compares the second and third elements, 3 and 18. Since 3 is already less than 18, no swap is needed. The algorithm just keeps moving down the list, repeating this logic. Eventually, each element is compared with its neighbor, and swaps are made when necessary. This continues until the list is sorted, and we get 1, 3, 18, 25, 30. In our example, we were lucky, and we were able to sort the list in just 1 pass. However, most of the time, bubble sort needs to go through the list multiple times before everything is in place. That's why it's not the fastest method, but it's a great way to understand how sorting works. The next type of sorting method is insertion sort. Insertion sort works by taking elements from a list one at a time and placing each into its correct position in a new sorted section of the list. It's like sorting playing cards in your hand as you pick them up. Let's use an example. Imagine we have the list 23, 1, 10, 5, 2, and we want to sort it in ascending order. Insertion sort starts by assuming the first element, 23, is already sorted and places it into a new array. Next, it looks at the second element, 1, and compares it with 23. Since 1 is smaller, it gets inserted before 23, forming 1, 23. Then it takes 10 and places it between 1 and 23, giving us 1, 10, 23. The fourth number, 5, is compared to the existing sorted array. It's greater than 1 but less than 10, so it's inserted between them. 1, 5, 10, 23. Lastly, 2 is compared and inserted between 1 and 5, resulting in a fully sorted list. 1, 2, 5, 10, 23. Insertion sort is useful for small data sets or nearly sorted data. It's efficient in situations where data arrives one item at a time, like live input from a user. It's also easy to implement and doesn't need extra memory, making it good for embedded systems. Next, merge sort is a divide and conquer algorithm that breaks a list into smaller and smaller halves, sorts each half, and then merges the pieces back together in the correct order. This makes it very efficient, especially with large lists. Let's use the example that 5, 2, 4, 7, 1, 3, 2, 6. First, merge sort splits this list in half into 5, 2, 4, 7, and 1, 3, 2, 6. Each half is then split again until every number stands alone as a list with one element. Now we start combining. 5 and 2 are compared and merged into 2, 5. 4 and 7 become 4, 7. These are then merged into 2, 4, 5, 7. On the right side, 1 and 3 become 1, 3, 2 and 6 become 2, 6. And these are merged into 1, 2, 3, 6. Finally, the two sorted halves, 2, 4, 5, 7, and 1, 2, 3, 6 are merged one last time. The result is a fully sorted list, 1, 2, 2, 3, 4, 5, 6, 7. Each merge step keeps the lists in order by comparing the smallest unmerged values. Merge sort is very useful for sorting large data sets because it has a consistent time performance of O(n) log n. It's especially helpful for data that can't be loaded all at once, like sorting files or data streams in external storage systems. One more type is heap sort, which converts a list into a binary tree. The largest element is taken out and added to a new sorted list repeatedly. First, we have to define what a binary tree is. A binary tree is a type of data structure used in computer science where each node has at most two children, usually referred to as the left child and the right child. Here's a quick breakdown. Each node stores some kind of value or data. Each node can point to two other nodes, one on the left, one on the right. The very top node is called the root. Nodes that don't have any children are called leaves. In this example, 10 is the root, 5 and 15 are children of 10, 2, 7, and 20 are leaf nodes. Now, heap sort is a comparison-based sorting algorithm that uses a binary heap data structure. It first builds a max heap, where the largest element is at the root. Then it swaps the root with the last element, reduces the heap size, and reheapifies until sorted. For example, the array 4, 3, 7, 1, 8, 5 is shown as an initial binary tree. This tree is then rearranged into a max heap, a binary tree where each parent is larger than its children. The value 8 is moved to the root, maintaining the max heap property. To explain more clearly, we start with the array 4, 3, 7, 1, 8, 5, and build a max heap bottom up. Starting at index 2, value 7, its child 5 is smaller, so no change. At index 1, value 3, children are 1 and 8. Since 8 is larger, we swap 3 and 8, resulting in 4, 8, 7, 1, 3, 5. Next, we heapify index 0, value 4, which has children 8 and 7. Since 8 is largest, we swap 4 with 8, yielding 8, 4, 7, 1, 3, 5. Now check index 1 where 4 moved. Its children 1 and 3 are smaller, so no further swaps. The array is now a valid max heap. After forming the max heap, we repeatedly remove the root, max value, swap it with the last element, and heapify the remaining tree. This ensures sorted output. The array becomes sorted in place without needing extra memory beyond the input. Heap sort is efficient for systems with constrained memory since it sorts in place and has ON log n, worst case time complexity. It's used in priority queues, real-time systems, and scenarios where consistent performance is needed, regardless of data order. The final sorting method is quicksort. Quicksort is a method by which we select a pivot element and split the other elements into two lists, whether they are less than or greater than the pivot. Quicksort is a divide and conquer algorithm. It picks a pivot and partitions the array into two groups. Values less than the pivot go left, values greater go right. It recursively sorts these subarrays, creating a fast and efficient overall sort. Quicksort is ideal for systems where average case speed is key and space is limited. It's widely used in databases, embedded systems, and libraries like Python's timsort function due to its in-place sorting and fast average speed. We start with array 9, 3, 5, 2, 6, 8, 6, 1, 3. The pivot is 3. Elements are split into two groups, less than or equal to 3 on the left, 3, 2, 6, 1, and greater than or equal to 3 on the right, 8, 5, 9, 6. The pivot 3 is placed in between. Now focus on the left subarray 3, 2, 6, 1. Pivot is 1. We again split. Less than or equal to 1 is 3, 6. Greater than or equal to 1 is 2. 1 becomes the new root between them. Continue with 3, 6. Pivot is 6. Partition to left, empty, right, 3. Now this subtree is sorted. Switch to the original right side 8, 5, 9, 6. Pivot is 6. Split less than or equal to 6 is 5. Greater than or equal to 6 is 8, 9. Place 6 in the middle. For 8, 9, pivot 8 splits it into greater than or equal to 8 is 9, less than or equal to 8 is empty. Recursively sorting these gives the final sorted subtree on this side. Each branch of the tree ends in sorted leaves, stitching together all branches, file 3, 1, 2, 3, 5, 6, 8, 9. Quicksort efficiently breaks a large task into smaller ones, sorts them, and reassembles for high performance in most real-world data sets. I hope that answered your question about the economy. I'll give my time back to the moderator now.
When you wake up, it's a new morning. The sun is shining, it's a new morning. You're going home.
On this day, with high hopes and brave hearts, in massive numbers, the American people have voted to make a new beginning.